Hello students, welcome to one more session of your 200 plus expected questions for your board exam. So basically we are on the day 9 of your expected questions. Let us see what are the most important inorganic questions which they're going to ask you. Let us start off with the session, students. Welcome to the session once again. Right, this is the first question which we have. Let us read the question and understand how to write in the exam. Got it, students? Yes. So the question, let us read the question first. Present the comparative account of the following. Okay, they're asking you to give a comparative study or comparative account of three different questions, right? So we have to write it in the comparative form only. Comparative, nothing but the difference form. Let us take the first question. What do they give me, students? Proton affinities of NH3 and phosphine. Okay, let me take a different pen for you all. I'm sorry for this. I'll take a white pen, or black is better, I think. Okay, chalo. Okay, what did they give me? Proton affinities of ammonia and phosphine. So basically, students, first of all, let us write ammonia here. Okay, then let us write phosphine here. So what did they say? Proton affinities. What is proton affinity, students? Basically, it's nothing but, right? So like affinity means attraction. Proton, attraction towards the proton. Correct, no, students? Yes. So they said to compare between proton affinity, which is having more. Okay, affinity is nothing but attraction. Let us take attraction towards proton. Attraction towards proton, the H plus. So basically, when I have to see both of them, right, this is the concept I need to understand and how to write in the exam. Got it? So when I take nitrogen, students, NH3, N, hydrogen, hydrogen and hydrogen, there is a lone pair of electron here. When I take PH3, P, hydrogen, hydrogen and hydrogen. Now what happens, students, here? The nitrogen size, whatever is there, first important concept here is nitrogen size is very small. Let us write the first point. So here in this case, what is the concept, students? Nitrogen size is small. Okay, nitrogen size is small. If nitrogen size is small, and if I compare the same thing here, size of phosphorus is big. Correct, no, students? Compared to that, size of phosphorus is big compared to nitrogen. Okay, now I'm comparing the sizes. The first point is over. The next point you have to remember here is when the size are, or when you're comparing both the sizes. What, students? Okay, let me write here. Sorry, let me write here. Okay, now when you're comparing both the sizes, what happens, students? In this case, in nitrogen, the lone pair of electrons, whatever is there, it is concentrated on a smaller region. Here, smaller atoms, a smaller region. But in case of phosphorus, it is spread over a larger space area. Correct? Now let us write in the exam that also. Correct? What should you write? In NH3, the lone pair of electrons, electrons is concentrated on how much area? Concentrated on smaller area or smaller region. Okay, this is what you understood. So if it is concentrated in smaller region, what happens, students? So density per atom, unit atom. So normally density is equal to mass by volume. Correct, students? Now what happened? Mass is smaller, right? So density per unit atom. If you take a small unit of this particular nitrogen atom, what will happen, students? Yeah. So its density is more. Density is directly related to the mass. Correct? So in ammonia, the lone pair of electron is concentrated in a smaller region. So what happens, student? So its density per unit volume or unit atom rather. Unit atom is more. Correct, students? So this is for which case? This is for NH3. Okay. Now, if I have to write for PH3, the same thing. What will happen, students? PH3, it is spread over a larger distance. Yes or no? See here. The size is larger. So, the density towards, or the density in phosphine is spread, and per unit atom also is less, no? Because it is more. Shall we write the same thing? Here we will write the second point. In pH3, the electrons are spread over larger area. Okay, when the electrons are spread over larger area, what is happening, students? What is happening, right? Proton, it has to accept, but here nitrogen tries to, because the electrons are here, it tries to pull this hydrogen, attract the proton towards it, because it is a smaller region, correct? No, so nitrogen will have more affinity compared to hydrogen, phosphine. Yes or no, students? Correct. So the hydrogen, it's going to pull towards itself. When it pulls towards itself, what is going to happen? Yeah, more affinity, correct, students? More attraction. It's a very small area. Perfectly, proton wants the electrons, nitrogen also pulls the proton, and more affinity. So what is the conclusion, students? In pH3, electrons are spread over, okay, I didn't complete this, on larger area, and density per unit atom is less. Correct, my students? Okay. So what is the conclusion? NH3 has more affinity than by pH3. Perfect. This is the first question, how you should write the comparative study. Now let us read. What are the physical states of nitrogen and phosphorus? Right. Simple question, students. What do they give me? Okay, before I take the next slide, I have 2 slides with me. I'll write that. So next question, physical question number 2. Okay, let us write the question number 2 here. So what did they ask me? Physical states. Okay, physical states. Of which one did they ask me, students? Physical states comparative of nitrogen they asked me. Then they've asked for phosphorus. Now, physical state is nothing, whether it is a solid, whether it is acting as what is the sort of what is its form in the at the room temperature, right? So basically, nitrogen is a gas. What is phosphorus, students? It is a waxy solid. Correct? Now, this phosphorus, what can it do? It can easily or readily, it can pass through the vapor state. Okay, this is already a gas, but phosphorus, it can readily pass through vapor state. Got it, students? It can go to the vapor state and it can exist in that. Got it? This is the second question. Easy question. Okay. Now let us read the third question. What did they give me? The shape of ClO2 and Cl2O. Very nice question. So next question we'll take, students. So question part 3. Right. I'm writing the third one. Structure of, because they asked me to compare, no? Okay. So structure of, what is that? First one, ClO2 and Cl2O. Got it, students? Okay. Now ClO2. Oxygen is a central atom. Oxygen. Here, chlorine is a central atom. Remember. In this case, 2 chlorines are here. In this case, 2 oxygens are here. In this case, the bond angle is 112 degrees centigrade. In this case, the bond angle is 180 degrees centigrade. Got it, students? Now, from here till here, the bond length is 170 picometer. From here till here, the bond angle is 147 picometer. Got it? I think you understood. Once again, I'll write it down. Right? So, bond angle, how much, students? In this case, bond angle is 112. In this case, bond angle is how much? 180 degrees. In this case, oxygen chlorine bond length is how much? 170 picometer. In this case, oxygen chlorine bond length is 147 picometer. Now, what is the shape of them? What is the shape? Both have V shape. Both are V-shaped molecules. V-shaped molecule. Okay. Similarity is this. Difference is this. Got it, students? So I think you've understood. 2 questions. First question, 3 parts are there in this. The first one, I have shown you how to write. Second part, this also I have shown you. Third also is just shown. So let us stick with all the 3 and you can write the same in the exam also. Got it, students? Now let us see one more. This is one more question which has 3 parts. What is that? Account for the following observations. Okay. What do they give me? The +2 oxidation state of lead. Okay, one second students, let me see. The +2 oxidation state of, okay, sorry, the +2 oxidation state of lead is more stable than +2 oxidation state of tin. That is what they've asked me. Correct, no students? So let us write the question. Question number 1. What does they say? +2 oxidation state of lead. One is lead, one is tin. I should not compare here. I have to write the reason. So no comparison here. Account for the following means giving reasons. Now check students. +2 oxidation state of lead. So first of all, when I take Pb, okay, your lead, what is the configuration, students? It is nothing but, most important, in lead we have 6s2 electrons. Whenever you see 6s electrons, what concept you are remembering? Inert pair effect. Right, my students, what concept? Inert pair effect. Reluctance of the s electrons to participate in the reaction. Inert pair effect. Correct? So 6s will not participate. Let us write inert pair effect is reluctance of s electrons to participate. Correct? To participate in the reaction. It will not participate in the reaction. Okay. They will not participate. Perfect. If they will not participate, what is left out to participate, students, in lead? Only we have 6p electrons. Correct? No? We only have in lead 6p2 electrons are there. Okay, 6p2 electrons are used. Okay. Now that's fine. Right. So what happens? Pb +2, whatever is there, it's formed under normal condition. Correct? No? 6p2 2 electrons are used. Hence, Pb +2 is formed under normal condition. Correct, no students? Okay, done. Now, what is the other thing they gave me? So the +2 oxidation state of lead is more stable. Normally, 2p electrons are taken. It is more stable. Now, +2 oxidation state of tin. Why it is less stable? That is what is important. Now, but in tin, what happens, students? The inert pair effect is not so strong. Larger size atom, no? Yeah. But in case of tin, what happened? In case of tin, okay. In case of tin, this +2, what happened is it is not so effective because it is a large size. It's so large. So in case of tin, what is going to happen? Size is increasing, right? Inert pair effect is not strong. It is not strong. Automatically tin is not so strong as so it can give only Sn +2 ion. Correct? No? It's not so strong. Hence it can not so strong means it like what happens is, see, normally understand, students, inert pair effect is not strong. So what is going to happen? It is not so prominent in tin to give only Sn +2. Hence it is not prominent in tin. That means, I'll tell you again, prominent in tin, Sn +2 to form Sn +2 ion. That means, what did they say? The question given to me is, lead, it is Pb +2 more stable than Sn +2. Pb +2 is more stable than Sn +2. I'm summarizing. Here, inert pair effect is there. Correct? Inert pair effect. In this case, no inert pair effect. Now tell me, when inert pair effect is there, 6s will not participate. Compulsory only 6p I am going to use and show +2. That's why this is more stable. It will utilize 6p2 and this will be more stable. But in case of Sn +2, no inert pair, means the inert pair effect is not prominent. So automatically it can show any other oxidation state, right? Not only Sn +2. So this is the reason, students. So Pb +2 is more stable because of inert pair effect and no other chance. That's why it is more stable than Sn +2. Got it done, students? Okay. Next question. Carbon dioxide is a gas, but SiO2 is a solid. Okay, what question did they give me? Carbon dioxide is a gas, but SiO2 is a solid. Let us write that. So what did they give me? I have to reason this. Second answer. Carbon dioxide is a gas. This is what they gave me. And they said SiO2 is a solid. This is what I have to reason. Now, when I take carbon dioxide, students, carbon, double bond O. When I take SiO2, silica, double bond O. In this case, carbon-carbon, what it forms, students? It forms p-pi bonds. Correct? This is pi bond. P-pi bonds are there in carbon. Okay, because it has carbon valency should be 4 tetravalent, so it forms p-pi bond. So because of this, what happens? It is a monomeric discrete molecule. Correct? No? Monomeric discrete molecule. It will exist like this only. Carbon, oxygen. So we call this as unit, single unit. Monomeric discrete molecule. Single unit only it forms. But in case of SiO2, what happens? This also, okay, this is a very large size. SiO, okay, SiO, again it's linked with one more, again it is linked with one more, like that. It is linked, it forms a giant molecule. It forms a giant molecule sheet like this. Correct? No? Why? Because it has a larger size. It is a larger size, right? Let us write SiO2 has a large size. Because of this, does it form p-pi bonding with oxygen? No. Does not form p-pi bond. Does not form p-pi bond with oxygen. Okay. Now, how is it satisfying its valency with 4 oxygen atoms? That's why it's going to form, SiO2 will form chain structure. You have to see, it's going to form a big chain structure like this. Si linked with oxygen, again linked with Si, again this oxygen is linked here, like that. A chain structure is formed. So what does it form? It forms a giant molecule. Okay, it forms a giant molecule. Now slowly I'm taking you into concept. It forms giant molecule. Now what did I say? First I said p-pi bond. It's going to form monomeric discrete molecules. Then here I said it can't form p-pi bonding. That's why it forms a giant molecule, big molecule. Correct, my students? Now here once again we will write one more point. Because of this, carbon dioxide molecule, simple, smaller. Here tetravalency is satisfied by, which structure? Satisfied by discrete monomeric molecule. Okay. In this case, students, in SiO2, how is the tetravalent structure? Satisfied. Tetravalency is satisfied by which one, students? By, yeah, it's been three-dimensional giant structure. Once again, three-dimensional giant structure. Right, students? So it's going to form a giant molecule. And you know, to break this SiO bond, how much energy I require, students, to break this bond? I require 368 kilojoules per mole. So much energy I require. Right? Because of this, this is discrete monomeric molecule, hence it exists as a gas. Only one unit. Here it is a three-dimensional giant structure, hence this is a solid. Understood, student? Understood? So in simple words, if I have to write, in simple words I have to write means in the summary if I have to write, I'll write only one word. I'll write only one word. Carbon dioxide as a gas because of one unit, monomeric unit. SiO2 is a solid because of giant units. This is the summary. Got it, students? Okay. Next question. Let us see the next question. Hydrogen fluoride has higher boiling point than hydrogen chloride. Very nice, easy question, students. They said hydrogen fluoride. Answer 3. Okay. Hydrogen fluoride has, what did they say? Once again, let me read. Hydrogen fluoride has higher boiling point. Okay. Let me write that. Has higher boiling point than HCl. Correct me, student. Higher boiling point than HCl. This is what they told. What is the reason? Now, in HF, this is electronegative. More electronegative means, students, more electronegative. So it's going to form hydrogen bonding. Yeah, fluorine. Okay, it's going to link with the hydrogen, more electronegative atom, right? Hydrogen. Okay, one oxygen, this fluorine, one hydrogen will be there, one oxygen will be there. Then hydrogen will be there, again fluorine will be there, again hydrogen will be there, like that HF. Okay, so hydrogen bonding between F and H. So here what is happening in HF? Most important, what do you have? Strong intermolecular hydrogen bonding. Strong intermolecular hydrogen bonding. Correct, students? Okay, now here in this case, HCl. What happened in HCl, students? In HCl, yeah, there is no hydrogen bonding. No hydrogen bonding. So because of this, because of the strong intermolecular hydrogen bonding, yeah, HF is a liquid. Because of what? Hydrogen bonding. Because this is more electronegative. And HCl is a gas. Why? Because of hydrogen bonding. This is absence of hydrogen bonding. Got it? Yes, students. Now you only tell me whichever has more hydrogen bonding, the boiling point will be more. HF, HCl. So I'll write conclusion. More hydrogen bonding, in this case, more boiling point. No hydrogen bonding, less boiling point, right? This is what is the thing, students. So thank you so much for watching. Thank you, students. Once again, thank you from Yuvani ma'am. Thank you so much. So meet you again. So meet you again, students. Please share the video. Again, I'm saying, please share the video. Always keep smiling, students. Always keep smiling. This is Yuvani ma'am. Take care. Bye-bye. Thank you so much. I'll meet you again with the next questions.